Hello everyone, welcome to Maths Club. Today we are going to discuss the volume of a solid generated by rotating a resin bounded between two curves when rotated about x-axis. And here we are going to use the disk or washer method. This is our third video of our series. So the example 3 we can take as find the volume of the solid generated by rotating a resin bounded between the curves y is equal to x square and x is equal to y cube, and when the bounded region is rotated about x-axis. So first again we have to draw both the curves and identify the bounded region. As the region is bounded by two curves, so to find out the region, first we need to find out point of intersection between the curves such that we can draw a proper picture. So here is the point of intersection between two curves. For that, we have to solve x and y by using these two equations. So if we substitute y from the first equation into the second equation, then the outcomes we'll get is x is equal to x square the whole cube. And if we open the bracket, that will gives us x is equal to x to the power 6. As you have to solve for the x, so we should take both of them into the same side of the equation. So the outcome becomes x to the power 6 minus x is equal to 0. And then take x common, which finally gives us x into x to the power 5 minus 1 is equal to 0. So to find the value of x, we need to make two different conclusions. First, x is equal to 0. And second, x to the power 5 minus 1 is equal to 0, which finally gives us x is equal to 1. Now to find the value of y, we need to put these values of the x into the equation. You can use any one of the equation, it doesn't matter. If we put x equal to 0, we will get y is equal to 0, and x is equal to 1, we will get y is equal to 1. So by combining these two, we can conclude our point of intersection between the curves are 0, 0, that is the origin, and 1, 1. So once we got these two point of intersections, now we can draw both the curves. To draw the curve, first we will start with x-axis and the y-axis. And here is the graph. X is equal to y cube. And the second graph, y is equal to x square. They are intersecting at the point 1, 1 and 0, 0. So the region which is bounded between the curves is this region. So we can shade this region. Now this region is going to get rotated about the x-axis to get the solid of rotations. We have to rotate both the curves about x-axis, and whenever you are rotating anything about the x-axis, then a mirror image about the x-axis is going to form. So for this curve x is equal to y cube, when it is rotated about the x-axis, then a mirror image of this curve will going to form below the x-axis. So here you can take the graph like this. And similarly, when this region y is equal to x square rotated about the x-axis, then again a mirror image of the graph will going to be formed. And to get the solid, we can draw the circle at the end of the point, which will joining both the end of the curve. So this is the approximate volume of the solid generated. Like in other cases, here also to find out the volume of the solid, we need to take the cross sections of the solid perpendicular to the axis of rotation, that is about the x-axis. But be careful, here the solid is a little bit different because this is actually a hollow solid. It is not a completely solid one because this portion is hollow. So here when you take the cross section, there will be two different circles formed. One is for the upper curve and another is for the lower curve. So we have to take both the circle together here. So let's take a better picture to understand the situations. So here the solid of revolutions we are going to take, and here is our solids, which is bounded between x equal to y cube and x square is equal to y, rotated about the x-axis. This is the rightmost portion of the solids, the yellow portions. This is the rightmost surface. This portion of the solid is actual solid, whereas this light shaded blue part is the vacuum portion. And to find out the volume of the solid, we have to take the cross section of this perpendicular to the axis of x, that is the axis of rotation. And when you take the cross section, there will be two circles formed for the inner curve x square is equal to y, and for the outer curve x is equal to y cube. Let's shade this intersection circular part. Here you can see one more thing. Here the intersection circular part is not a solid disk. It is rather a hollow disk, which is also known as the washer or ring. That's why this method is known as the disk or washer method. Sometimes it is also called as disk or ring method. And this is the point where the center of the rightmost part line, and this point is your 1, 0. Now, like the before, we have to take the volume of this disk or washer and you have to integrate it from the leftmost point, that is origin, which is 0, 0, to the rightmost point, that is 1, 0. So how the volume of the disk can be calculated? Let's take a comparatively simpler picture to understand how the volume of the solid can be calculated. So here is the solid without any kind of shading, which will make the things comparatively easier to understand. Let width of the disk, which is parallel to x-axis, is delta x. So this portion we can take as delta x. Now if we look the radius, the disks actually have two different radius. One is the inner radius r and is the outer radius capital R. And as the radius is actually distance from the axis of rotation, that is the x-axis, so the r, which is also the distance from the x-axis, will be equal to the y of the curves. So both the r, small r, and the capital R can be equated with y. But be careful, both the y will not going to be same, because the y comes from different curves. Now, if we're trying to find out the area of the disk, which can be denoted by delta A, then as this is the hollow disk, so it will be pi, the outer radius, capital R square, minus inner radius, smaller square. Now, capital R is equal to y, and that y comes from the curve x is equal to y cube, and x is equal to y cube gives you y is equal to x to the power 1 by 3. So if you put these values of the y into the capital R, then it's become x to the power 1 by 3. And if you look at the smaller y comes from the curve y is equal to x squared. So this smaller can be equated with x squared. By substituting both the r into this delta A, we can finally get pi into x to the power 1 by 3 whole square minus small r square, that is your x square whole square. Just we need to simplify a little bit. Finally, the delta A gives us pi into x to the power 2 by 3 minus x to the power 4. Now, the volume of the disk, which can be given by delta V, which can be written as delta A, the area, multiplied by the width, that is delta x. So finally, the volume of the disk we are getting as pi x to the power 2 by 3 minus x to the power 4 multiplied by delta x. And here x is varying from the point origin to this point 1 comma 0. So here x is varying from 0 to 1. So to find out the volume of the entire solid, you have to integrate the volume of the disk from 0 to 1. So finally you can conclude volume of solid V is equal to integration of 0 to 1 delta V. By substituting delta V, we are getting 0 to 1 pi x to the power 2 by 3 minus x to the power 4 dx of it. Now by using the basic formula of the integration of x to the power n dx is equal to x to the power n plus 1 divided by n plus 1. We'll get, this is just pi into x to the power 2 by 3 plus 1 whole divided by 2 by 3 plus 1 minus x to the power 4 plus 1 divided by 4 plus 1, and the limits are 0 to 1. Now simply we have to calculate this to find out the final volume of the solid. So finally the V comes as, by substituting the values of 1, because 0 will make both the terms 0. So pi into 3 by 5 minus 1 by 5, which finally gives us 2 pi by 5. So the volume of the solid generated is 2 pi by 5. Hope you understand the process. But before we are winding up, there are two important things you have to remember. That is, when we are rotating the volume about the x-axis, then integration have to be done with respect to the x, and when you are rotating about the y-axis, the integration have to be done with respect to y. And while we are integrating with respect to x, all the variable have to be in terms of x, and while we are integrating with respect to the y, all the variable have to be in terms of y. In the next video, we are going to discuss the volume of rotation about the y-axis when region bounded between two curves. So that's all for today. Thank you for joining. Have a nice day.